Today we are starting a series of talks, actually, which will be about the unitary groups rather than the symmetric group, which was the topic in the last month. And the first one in the series is Soren Eilers from Copenhagen, who will talk about matrix stability of crystallographic groups. And I'm sure he will explain, but he will concentrate on the operator norm stability.
Yeah, so
Soren, the stage is yours. Thank you very much.
So thank you, Alex, for the invitation. I'm very happy and honored to speak here. So as Alex said, this is only about operator norm, and it's sort of really by necessity, as I'll point out, because I'm using Cstar algebraic methods, and we are somehow tied with the operator norm. So that's might as well say that from the beginning. I don't know how to take any of this to other norms. So I'm going to show you the proof in the hope that perhaps you can use some of it, or that maybe it's inspiring for something slightly, I mean, it's not going to go the same way, I don't think, I'm afraid. Okay, so let me see if I can move. So I set it up very basically. So I have a theorem that I want to show you. I want to explain how it's proved. It's a theorem I proved with Adam Sorensen and Tanja Schulman. So Schulman gave a talk in the last, she does all kinds of things in this business. We were interested in a certain property of Cstar algebras that I'm going to define to you called semiprotectivity. And we looked at it for Cstar algebras associated to groups. And then you can sort of backtrack and see what this means for the group. And this is what I'm doing. Okay, so let me see if I can move ahead. So here's a big slide. So just so we agree, we take a finitely generated group, and then we represent it into unitaries of some matrices. And we just require that a representation just means that the relations that we're interested in will get sent to the unitary one. And then we can talk about a delta representation, saying that this is not hitting one on the nose, but it has an error of delta. And then, of course, as soon as I'm saying that, I need to explain what I mean by the norm. And the norm that I'm using is the operator norm that I get by taking the Euclidean norm on Cn. Right. So I'm simply when I'm measuring the difference between unitaries, I will look at the supremum of what happens when you apply the difference to all the vectors of norm 1. So that's a perfectly reasonable norm, but of course there are other perfectly reasonable norms. And as I already said, I am afraid I don't have so much to say about those. And then we can say that if we have generation relations, we can say that they are matrix stable if whenever there's an epsilon given, you can find a delta, so that if you have a delta representation, it is epsilon close to an honest representation. And this has to be uniform in the matrices. So I'm not asking for the size of the matrices before deciding what the delta is. So that's very important in all of this. And in fact, if you did have the matrix size, then you would get much more positive results. But on the other hand, they would be less useful. So that's just the way it's set up. And the way I've defined it, it looks as though this depends on the concrete choice of generators and relations. But it's going to fall out from something I'm doing. I mean, it's not so hard to see, but it's going to fall out for something I'm doing in a second, that it depends only on the group, not on the concrete choice of generators and relations. So are you going to yell at me if you want to ask something, or you write something in the chat? I'll keep it open. So just stop me.
No, that's usually the system here that we yell.
That's great. I like that. Okay, so a crystallographic group is, well, I mean, there's many definitions, but you could take the isomorphisms of Rn, and then you take a discrete normal subgroup that has a compact quotient. That's the sort of dry definition of crystallographic groups. But of course, usually you think of them as the group of symmetries of some pattern or tiling or something like that that you have in Rn. And by some classical results, Bieberbach and Sassenhaus, there's only finitely many crystallographic groups of each rank. And they are computed pretty far further than what I wrote here. And I'm not going to say anything about the 28 million, well, almost 29 million different groups of rank 6. I'm actually only going to say something about the first 19 ones. So, I mean, the two groups that you get at rank 1, which is just Z, and the infinite dihedral group. And then for rank 2, we have the wallpaper groups, and that's what I mainly want to talk about. And then you can do this in higher dimensions. And the point here is only that these are sort of listable. And the theorem that I want to show you the proof of is that there are exactly 14 matrix stable crystallographic groups. So all of the ones in rank 1, none of the ones in rank 3 and above, and then 12 out of the 17 wallpaper groups. And the ones, let me just give that away right away. So the ones that become matrix stable is the one that's have some sort of glide reflection. So the pure rotational examples are the ones that are not matrix stable. Okay, so and this, I mean, personally, I like this project because it somehow it turns out that when you do this particular special case of the many things that I did with Tanya and Adam, this particular case goes back to something that I did when I just got out of grad school. So this is really the first paper. I was by far the junior author. Gerd Peterson was my advisor. Terry Loring is at University of New Mexico. And the second paper, I'm by far the senior author. So this is somehow, that's, I guess, life. And I want to show you the more or less the complete proof of the positive results. So the fact that these 12 or 14 groups are matrix stable. And I have to say that somehow, you know, it's the stars align kind of proof that things just fit together very nicely, and it sort of falls out very beautifully. And this, of course, is nice, but it also has the feeling. I mean, I also have to say that I don't really know how to generalize this in any reasonable way. As I said, we can only say something about the operator norm, and then at the end of the talk, I want to show you, I mean, the negative results. We have an approach in our paper which is somewhat ad hoc, and then more recently, Mario Stadalat, who will also speak in the seminar in a couple of times, he found a better way of doing it. So he sort of has a more systematic way of addressing this problem. So I'll use his way. So that's not the way that we use it. Okay.
He will talk in 2 weeks.
In 2 weeks, okay, yeah, and I think he will probably. I mean, I don't know if he's going to cover this particular, but it's sort of the same thing that he's managed to clarify the obstructions to matrix stability in terms of K-theory, where we in our paper we have a sort of an ad hoc winding number argument, which is not so K-theoretical and less general. So I think clearly Marius has the best way of doing this. Okay, so so a C-star algebra is just an algebra over the complex numbers, which has an involution, hence the star, and then it has it's also Banach space, and so there's a complete norm, and it satisfies that the norm of xy is less than the norm of x times the norm of y, so it's a Banach algebra, and then the C-star relation is that the norm of x star is the same as the norm of x. And a very easy example, which somehow is actually a universal example, is that you take a Hilbert space and you look at the bounded operators on a Hilbert space. Then the star is just the adjoint operation, and the norm will be the operator norm. And then all of these things will be true. And actually, the Gelfand-Neumann-Siegel theorem says that every C-star algebra can be embedded into B of H. So that's what I mean by saying that this is a universal example. You can also take a finite dimensional Hilbert space or an n-dimensional Hilbert space, and then of course you just get the matrices, and then the inherited norm that I get is the operator norm. So that explains why I have to look at the operator norm. And actually you can prove that the norm of a Cstar algebra is unique in the sense that you can determine the norm of an element entirely from the algebraic structure of the Cstar algebra using the spectrum. So you have only one choice of putting only one chance of putting a norm on a Cstar algebra, and so that means that I have to use the norm that I get from B of H. So that's really why I'm so tied in with the operator norm. You can also have a commutative Cstar algebra, and if that has a unit, then it's just going to be the continuous functions on some compact Hausdorff space. If it's not unital, then it's the functions vanishing at infinity on a locally compact Hausdorff space. Okay, so I mean, I don't need a lot of, I'm doing something fairly directed, so I don't need a lot of Cstar algebra theory here, but this is sort of where I come from, so it sort of underlines all of my thinking. Some very basic operations you can do if you have a sequence of Cstar algebras. You can take the direct sum, then you just take the max norm and you'd use the pointwise operations. And you can also do this sort of infinitely, and then you have two ways of doing it. Either you take a product where you sort of have that the elements have to be bounded in norm, or you take a sum or an orthogonal sum, or so that's usually written with an O plus, and then the norms have to go to 0. Now that doesn't have a unit, and actually you can prove that it's an ideal. The sum is an ideal in the product, and that's going to be important for something that we're going to do. So I think that's actually all that I need here, except I want to point out that if you have a finite dimensional Cstar algebra, it's going to come from a direct sum of matrix algebras. That's another basic result. I have a feeling I'm forgetting something. Okay, I'll come back to it. And now I have to spring this on you, which is a little bit weird. This is the notion of a semi-projective Cstar algebra. So this may look like a strange definition. It was invented by Bruce Black at our University of Reno in 1985. And it has somehow grown into a standard concept in Cstar algebra theory. We use it a lot. We use it in particular in classification, which I'm not going to talk about, but if you want to classify Cstar algebras up to K-theory, this is a very useful concept. And the way you should think about it is kind of a generalization of the concept of an absolute neighborhood retract, an A&R in topology. So essentially what I'm saying is that I want to have some sort of projectivity property out of A. So I have a map from A into B modulo the union of some ideals. And then I'm not requiring that I can lift the map all the way. I'm just requiring that I can lift it to some finite stage. So what this means is that that it's a property of A being semi-projective. That means that whenever I have a setup with B and inside B an increasing sequence of ideals, then if I have a given map into B of the limit, which is just the closure of the union of these ideals, then I can lift it not the whole way to B, not to the B mod, the first ideal, but to some stage. And this turns out, I mean, there's also a concept of projectivity for Cstar algebras, but this is extremely rare. This turns out to be what you want to look at. And I'm gonna black box this concept a little bit because showing you the details of this is a little bit tricky. So I don't think I'm gonna do that, but essentially I want to explain to you that this notion is relevant when it comes to matrix stability, but also that it's too strong. And so we will talk about a weaker version of this later on in the talk. So for instance, if you want to know if B of H is semi-projective, then Black and R worked this out. So this only happens in the finite dimensional case. But if you do have the finite dimensional case, so matrices, then it is semi-projective. Actually, that goes back to Glim. And then also, if you want to know if a commutative unital Cstar algebra is semi-projective, that exactly becomes the A&R condition, and also finite that the Hausdorff dimension of the space has to be at most 1.
Can you repeat? I didn't get what is A&R again? You said something, but
It's called, I forget if it's absolute or approximate neighborhood retract, but it somehow means that you have a space, so that whenever you have a neighborhood of it, you can find a smaller neighborhood that retracts back to the space. So it sort of has to be locally trivial. So something which doesn't have it would be like a Warsaw circle or something like that. An ordinary circle is fine, because you cannot take the whole space and retract it into the circle, but there's a neighborhood, like a tubular neighborhood of the circle that you can. So it sort of means that you can go back to your space, and that's essentially what this means. Then if you want to check what you can sort of take the dual of the notion of being an A and R, and that actually becomes the same as semiprotectivity, except that you would have to ask for B and the I's to be commutative. So if you just take the definition of A and R, that's the same as what I have in this diagram, except for the B's and the I's necessarily to be commutative. But then when you throw in the non-commutativity, which of course is essential here, that also gives you the dimension condition. So this is somehow, so I mean, these are somewhat weird concepts. They've been around for a long time, and we know quite a lot about them. And I want to emphasize in the talk that somehow we can use this to prove stability results, but also that if we only work with semi-projective Cstar algebras, we're not going to get very far. So that's somehow how I would like you to think of this as something very nice, which doesn't happen so often.
Just I'm a bit confused here. Your groups you're going to look at eventually are very close to abelian. So
yes.
At a finite extension. So the whole issue is that part of the problem?
This is very, I mean, that's
the entire problem.
So one of the reasons I can say something about this, as because these groups are very close to abelian, the Cstar algebras are going to be very close to commutative.
To continuous functions on something. Okay.
Yes. But not entirely. I mean,
and these problems just, so I'm not familiar with all this. If the group were a tessellation of hyperbolic space, so there would be like a surface group or something, then what, and maybe you work with a reduced Cstar algebra, what happens there, do you know?
So for the full group Cstar algebra, for the surface groups, they fail to be.
I'm sure, but the reduced one? The L2 reduced, that's kind of
right.
One I like very much, where you have this kind of Kaplansky-Cadison conjectures are true in many cases. This work of vocalescu, that has no bearing on this.
I don't know.
What's the question? Whether they are semi-projective, or the question is about stability?
I'm curious in terms of Cstar algebra. So there's a theorem that I think one of these guys, Efros or somebody, proved that the circles, he points out that in one of these realization, the circle is connected, and it proves the following amazing statement, that if you have in a reduced Cstar algebra of certain type of groups which don't have elements of finite order, the spectrum of any element must be an interval. Reduced spectrum, it has to be an interval, can't have gaps. And I've never been able to prove that elementarily. I've used it, but I don't have an easy proof. So I'm trying to understand where the beef of the Cstar algebras is used. And there's a theorem of number of people, including vocalescu, which is critical. And I'm just trying to understand. So this is very much abelian, what you're doing. Very close to abelian. Yeah. Okay.
Yeah, that's definitely have to admit that. And actually, I'm going to show you what the Cstar algebras look like for some of these crystallographic groups. You can draw them. They're going to be non-commutative, but in a very controlled way. So this is definitely, it sort of goes into the whole machinery. And also, these groups are so close to abelian that the reduced and the full will be the same.
By the way, but could I ask a variant on what I originally thought Peter was asking, which is, so if you were to take a closed hyperbolic surface right? There are, because of the original vocalescu examples on the torus, you don't have stability there.
Right.
But do you know that that's the only obstruction, right? That if you have, say, the winding number equal to 0, then you could approximately, because surfaces are also very close geometrically to these things that are two-dimensional orbifolds, right? It's just that you're looking at the ones that are genus 1, and the higher genus ones, you would expect to have similar stability properties, except that they'll have to be the ones that have a fundamental class.
Right. I don't know the answer to that, but I know the answer if you do the original vocalescu matrices, and I'm coming to, but that if the winding number obstruction vanishes, then you do get stability. So I think this is, I wouldn't know how to do this for surface groups, but something like that might be possible. I don't know.
All right. Okay. Well, sorry for interrupting.
Tanya here, she might know. Okay. Well, let's. I'll move on. But yeah, I'm afraid I don't know the answer to those questions. But and I agree they're good. I wish I knew. So okay. So let me just tell you what we mean by representation in the Cstar algebra. I mean, this is sort of the same, but we just take. I mean, now we would probably have something like star polynomials in generators, and then the relations look like that, and then a representation. I'm going to cheat a little bit because there's an issue with the boundedness of a representation, which has to do with the fact that a star homomorphism, I mean, something that respects all the structure of a Cstar algebra, has to be norm reducing. So this means that if a general representation of a certain element were to be unbounded, we wouldn't be able to define a Cstar algebra on it. So I'm doing something slightly non-standard, and I'm putting in the condition that whenever I'm representing onto a Cstar algebra, the norm of all the generators is 1 or less. So very often when we're working with groups, we have unitaries, and then it's automatic. But I mean, I'll just put that in as an explicit condition, and then of course it means that the relations are killed. And then there's a fairly easily to see there's a universal Cstar algebra that has the property that that comes with a canonical copy of the generators, such that any representation lifts through the Cstar algebra in a unique way. So there's a star homomorphism from this universal Cstar algebra to A, and the existence of this is a standard. You sort of do a free type of Cstar algebra and you mod out. So this is not so surprising. The thing that is perhaps a little bit surprising is that if you have fairly nice relations, you can work out these Cstar algebras, and that's where I'm cheating, because my groups will be so close to abelian that actually I can work out what the Cstar algebras are. But of course, you could make it very easy for yourself by taking a commutative example, because if your generators commute, so this time, of course, since it's a star algebra, I have to have not only my generators but also the adjoints of the generators. They have to commute. But if, for instance, I ask for H to be a self-adjoint, then I'm essentially looking for the universal Cstar algebra given by a self-adjoint element of norm less than 1. Now you can just look at the spectrum, so that's the same as the continuous functions on the spectrum. And if you have more than one of these operators and they are asked to commute, which I sort of put in, then it's just a joint spectrum of these objects. So you can easily compute for the universal Cstar algebra for a self-adjoint is the interval, continuous functions on the interval, for unitaries and continuous functions on the torus, and so on. And by the description of semiprotectivity, you can see that the first two are semiprojective because these are one-dimensional spaces, but they're not semiprojective below because they're not semiprojective. And by the way, we always write, so in my world, we always write the relations as something with an equality. So I hope you don't mind that I put it this way. That's the same. So you can also, of course, make some examples from groups, and then you just put in a relation saying that you have to have unitaries, And then, of course, if that's the only thing, then you get C of t. If you have two commuting unitaries, you get C of t squared. And then I have some other examples. Like I'm asking for my unitaries to be essentially self-adjoint. And so that's essentially what I have. So I have a little computer problem here. So I just need to do something. Sorry. It's just my computer is a little bit old and it fills up if I'm not careful. So I just removed some things. Okay, so so what a better way of thinking of this is that you somehow say, I'm talking about the universal Cstar algebras of some generators and relations, where I will just, if I have a group given by generators and relations, I will just check the generators and I will translate them to be some unitaries. And then I'm putting in the relation that they have to be unitaries. And then I just translate the original relations into relations on the unitaries. That gives me a Cstar algebra, the universal Cstar algebra of these generators and relations. And this is a special case of the group Cstar algebra construction. So there's, you can associate a Cstar algebra to any group. In this simple-minded case, you can do it this way. And as Peter pointed out, you have to be careful because there's more than one group Cstar algebra. There's a reduced and a full one, but we're only working with groups that are so nice that this will be the same. So I don't have to worry about it. I guess if I had to choose, this was the full choice because it's somehow the universal one. Okay, so this is just the group Cstar algebra of Z square of the infinite dihedral group, and the example that I have is one of the crystallographic groups in the notation of Cstar and Moser. This is called PG, but this is also it's also Baumschlag-Solitar group. It's also a surface group, just at a very low level. Okay, so here's the point, that these groups are so close to being abelian that I can actually write them up. Right. So even in the non-commutative case, these are fairly easily described. Actually, there's an ancient result by Thoma saying that a virtually abelian group will give you a subhomogeneous Cstar algebra, which means that all the irreducible representations are into matrices of a certain fixed size, and vice versa. But here it's a little bit nicer, and I thought maybe I should try to draw this instead of these complicated setups here. So maybe I hope I can show you this. Just need to type my code like this. So I mean, so the way I would like to think about it is that blue for me here now means 2 by 2 matrices, right? And then the one that corresponds to the infinite dihedral group is just a function, a continuous function from the unit interval into the 2 by 2 matrices, but it is special at the endpoint. So I use, oops, let's do that. So I use purple there. So it's special at the endpoints. The way it looks is that it has to have this form here and this form here. So it's diagonal at the ends, and then in the middle it's the 2 by 2 matrices. And you get this by just looking at all the irreducible representations. They have to have this dimension or less, and then you just stick them all together using the topology of the underlying space. If I was to do the same with PG, it's a little bit more complicated because it now becomes two-dimensional. So here I have like a whole box, which is continuous functions from the unit square into 2 by 2 matrices, and then it's going to be like a torus in the sense that I identify these two sides here and identify these two sides here. But actually on those sides, it has to be diagonal in the same sense as it was upstairs. But the way it's set up, it's actually that these, I don't know if this drawing helps you, but what I mean by this is that just like before, it's like a torus in the sense that they have to match up at the two vertical ends, but at these two vertical ends, they are scalar. And then there's a twist, so that when you start from the beginning and you go up, the two eigenvalues are intertwined. So this is actually one circle that you get gluing it together this way. So, I mean, you can just work it out and find the representations and see what it looks like. This is all sort of basic, but of course, very easily to do wrong, as I've done many times. But this sort of helps in order to say something about these objects. And we had, when I worked with Loring and Peterson many years ago, we came up with some language about this. So essentially, the way we think about it is that we will say a finite dimensional Cstar algebra, which is just a sum of matrices, we'll call it a zero-dimensional non-commutative CW complex. I don't know if that's a good name. That's what we chose. It's a long time ago. And then a one-dimensional NCCW lives on there's a typo. It lives on the there should have been an n up here, right? So this, it's not the interval, it's n copies of the interval. I'll fix it before I hand over the slides. And then, so what essentially, like in the example that I showed you, a one-dimensional NCCW is something that lives on the interval and takes values in some finite dimensional Cstar algebra, except that it's a pullback, so it has some boundary conditions. So you can make a circle, you can put things down in dimension, you can do a mix of it. That's what it means to be a one-dimensional NCCW. And then you could do the same in 2 dimensions. That's another example that I showed you. And the point is really that you sort of take all the functions into, in my case, the 2x2 matrices, and then some boundary conditions that have to come from a one-dimensional NCCW. And so you can sort of do this inductively. And then we proved that if you had a one-dimensional NCCW, that would always be semiprotective. This is somehow, this is a hard proof. There has been some improvement actually by Dominic Enders, and he also he found a somewhat nicer proof, and he also proved that it was an if and only if statement. So essentially, I mean, these are Cstar algebras that are not commutative, but again, they're commutative enough that they behave when it comes to semiprotectivity, because these spaces are always RANR, that they behave enough like the commutative case. So you have semiprotectivity in the one-dimensional case, not in the n-dimensional case for bigger n. So this sort of tells me something about these examples, right? Because we worked out what the Cstar algebras look like. So in the infinite dihedral group, which has rank 1, we get semiprotectivity, and for PG, which has rank 2, we get not semiprotectivity. And then I'm conjecturing, I mean, that has to be true, but that the Cstar algebra for any crystallographic group of rank n is an NCCW of dimension n. I don't know this to be true. Actually, it's not as easy as you might think, but fortunately for me, there was a master's thesis from Boulder, 99, by a guy called McAllister, who works out that for the crystallographic groups of rank less than 2, they are all NCCWs, and he actually works out how you make them. So this has been worked out for me. Okay, now I'm getting ready to talk about stability for Cstar algebras, which we haven't touched on yet, but it's the obvious thing. If I have a representation, then we will say that it's, I mean, a representation just means that you kill off all the relations, and the delta representation, you kill them off up to delta. Delta could be anything here. And then we will say that some generators and relations are matrix stable if for all epsilon there's a delta, so that if I have a delta representation into some matrices, then there is an honest representation epsilon away from that. Delta has to be chosen to epsilon uniformly in n, And for Cstar algebraists, I think this all started with a question in Monthly by Rosenthal, who asked if you have a self-adjoint, a pair of self-adjoint operators that commute, is that matrix stable? And Helmholtz proved, I mean, actually, it's not entirely clear from his question if he wants a uniform solution or not. But Helmholtz proved that there was a non-uniform solution, which is fairly easy. And then Percy and Shields, they actually worked out what the quantification would have to be. But you can see that depends on n. And so for many years, it was open if you could do this in a uniform way, which is what I'm asking for. Now, as we've heard also from Peter, there very early in the theory, it was realized that there's a problem here for unitaries. These are the famous vocalescu matrices. So these are concrete matrices that are unitaries, where vocalescu proved that when you increase the size of the matrices, they will commute better and better, because these are sort of down the diagonal. I have roots of unity, and then I have a shift, so that is pretty good. But then he also proved that the distance to any honestly commuting pair of unitaries remains bounded away from 0. Actually, it's 2. And there's many proofs of this, right? Many ways of doing this. I think my favorite proof is the one that was given by Exel and Loring, which goes through winding numbers of a certain determinant. Voiculescu used index theory, as I recall, but it's a third proof that I want to talk about in a second, because that sort of helps me explain what happens in my case. But so this shows you, of course, that in a very dramatic way, the relations defining a commuting pair of unitaries is not matrix stable. But actually, Huochen Lin from the University of Oregon, he proved in '94 that the question asked by Rosenthal has an affirmative answer. So that is matrix stable. So you can choose, given epsilon, you can choose your delta in a way which does not depend on the matrix side. And you can also see now that, as we've seen, that these two Cstar algebras are not semi-projective. So I'm not going to get, so this means that semi-projectivity is too much to ask for. You don't need it for matrix stability as what Lin is explaining. And that's exactly the core of the proof that has to do with a certain dimension reduction technique that I want to show you. Now, following Lin, it's probably older than that, I want to recast matrix stability of some generators and relations into a lifting problem. So what I mean by this diagram here is that, suppose that I have a universal Cstar algebra and I have a given map called gamma that goes to product modulo sum of some matrices. Then I'm claiming that I have matrix stability if and only if I can find a star homomorphism that lifts this into the product alone. And the proof is sort of fairly straightforward. So let me just sort of quickly take you through it. So, what does this mean, right? So it means that I have a map from gamma from the universal Cstar algebra. So that means in particular, I have some honest representations of the generators into the product modulo sum. So there's some elements inside the product modulo sum, and I recall to you that I asked for those to have norm no more than 1. It's easy to prove elements, to lift elements of norm no more than 1 to elements of norm no more than 1 by using spectral theory, essentially. And then, so you can always lift your elements to that. And that's what I'm going to do. So I'm just going to take any lift of the generators to the product. Now, that doesn't have to behave very well with respect to the generators, but it can't be too bad, right? Because this was the vertical representation was an honest on the nose representation, the relations get sent to 0. So this means when I lift them, that those lifts will be sent to the ideal. And the ideal precisely was defined such that the elements went to 0 in norm. So this means that if I just say, let's just take these representations and I will call them delta I representations, with delta I chosen as small as it can be. So I just take the defect of being honest representations, and I call that delta I. And then delta I has to go to 0, of course, in a way that I can't really control, but it has to go to 0. Right? And then
when you wrote this notion of direct sum, you don't mean really the direct sum that after a while it's 0. You mean that it's that they converge to 0.
Exactly.
That's what you mean, right?
Yes, yes. So the infinite direct sum means that it goes to 0. That's what we usually use. It's a little weird. Yeah, but I mean that's important because.
Okay, so it's good that I asked, because some other areas of Mathematica, this means that they are almost always 0. Okay.
Yes, yes, yes. I apologize for this. It's not a good notation, but we all use it. So the point is that, yeah. So, and of course I would need something like this because I have completeness, right? So I mean I have to live with some sort of infinity like that. But so the point is that I don't know that it's eventually 0, but I know it goes to 0. And that's good enough, right? Because then I can sort of do a diagonal argument. I'm sure you've seen things like this before, but essentially what I would do is I take epsilon to be 1 over k. Then by assumption, I have matrix stable relations. So this means that given that epsilon, there's a delta, so that if I have something which is close enough to being a representation, then it is epsilon away from an honest representation. And of course, I cannot do this in the beginning where the error is too big, but I can do it eventually because I know that the values go to 0. And then I could just sort of keep on doing this and stick things together in a like what I have down here. And you can see that I'm putting in zeros in the beginning, because in the beginning my representation will be very bad, and I don't know that this is close in any sense to any honest representation, but that doesn't matter. I can just put in zeros in the beginning because I'm mapping into product modulo sum. So what I do on a finite number of them will not matter because it gets modded out. So that's why I can do this. So I mean, I'm showing you this proof because this is really essential for all that follows. I'm also showing it to you because I'm sure you're going to ask me, do I have any concrete information about the relation between epsilon and delta? And I'm going to have to say no, precisely because of this. I'm sort of building this into a product modulo sum where I completely lose control of the relation between epsilon and delta. So that's another problem here. Now for the Lind's theorem, there's work by Hastings actually proving a concrete relation between epsilon and delta, but it sort of goes a different way, and I wouldn't know how to do this here, even though that might actually be an interesting project that haven't excuse me, thought so much about. And the other way is sort of the same. You just, if it's not matrix stable, then there's an epsilon so that you can get representations getting better and better, which stays away from that up to epsilon, and then you can find the lift and you get a contradiction. Okay, so I mean, so this result, of course, first of all, it says that when you ask for matrix stability for some generators and relations, you're really asking a question not for the generators and relations, but about the Cstar algebra. This, of course, is extremely important for all of Cstar algebra, I mean, all of operator algebra. The idea is that instead of sort of looking at one operator at the time, you look at the whole algebra, because then you have many pictures of the same thing. And that gives you the strength of being able to jump back and forth. So this is a very sort of Cstar algebraic way of thinking. And it also shows very easily that if I have semiprotectivity, then I get matrix stability, because essentially the lifting property that I have for semiprotectivity means that, suppose I take B to be the infinite product, and then my IKs are, 1 copy, 2 copies, 3 copies, and so on. The union of that, since I close off, is exactly what I call the direct sum. And so I have a given map into that, then I can lift it to some stage. What that means actually is that I can lift it not to the infinite sum from the very beginning, but the infinite sum from some stage and onwards. But that doesn't matter. I will just pad with zeros like I just did. I can lift it all the way up. So semi-protectivity gives me matrix stability. And furthermore, if we're working with groups, it doesn't matter these extra relations that I had to put in order to make sure that I got a unitary. You don't have to ask for those explicitly in the matrix stability, because CFT is semi-projective, and that means that you have stability properties for a unitary in a very strong way. So if you have something which is just slightly close to a unitary, you can find, not so far from it, an honest unitary. So the matrix stability property that I showed you for groups is actually the same as the matrix stability property for the group converted into Cstar algebra relations. And so you can see this also for a lifting property for the group Cstar algebra. Right? So I've been able to recode the stability property of these groups. This is completely general, but of course the problem is that if we have a very complicated group, then I'm probably not going to be able to tell you if you have this property for the group Cstar algebra. Now, that's why I need nice groups for what follows. Okay, so what do I know this far? So I know that the rank 1 crystallographic groups, they gave me semi-protective Cstar algebras. So that means in particular they are matrix stable. I know one rank 2 crystallographic group, namely the Z2, which is not matrix stable because it translates to commuting unitaries, and vocalescu explained to us we have a problem there. And then actually you can use that in order to prove that if you have a higher rank, then it's never matrix stable, because inside the general copy of the interval to the n, you can embed your torus there, and then you can find a counterexample this way. So that's
can you explain this? No, I don't see that. Why for higher rank this gives you automatically?
Yeah. So the point is that you can. I mean, this is not trivial, but you can prove that because you can take your two torus and put it inside the generic cell of the NCC. Actually, I don't know it's an NCCW, but I always know that inside a rank n crystallographic group, there is a big sort of area where you have the continuous functions from that into some matrices, and then using that you can define a map which is based on the vocalescu matrices, and then which is not liftable. So, but I mean, you need to keep. I'm not saying it's obvious, but you need to keep track of how it's put in.
Is it possible to see it group theoretically somehow, that you have in some almost representations?
Isn't it true that if you have a subgroup of finite index which is not p-stable, not norm-stable, then you are not norm-stable? This is kind of the question.
Absolutely not. Absolutely not, because the main theorem is going to tell us if there are 5 crystallographic groups of rank 2 which are stable, even though Z cross Z is not stable. So in particular, it shows that, which is somewhat surprising, and or at least we don't know this for other types of norm either way.
Right.
But that's not a good enough reason for to give negative answer to the other. But somehow,
maybe just one.
I wouldn't know how to do it without the Cstar algebras.
I mean, there's just one case that might be helpful to understand, that, the infinite dihedral group, right, that contains Z with index 2, right? It was one of your initial examples. And then just take the product of it n times. So that doesn't look like it contains a torus, right? It looks like it's just a cube, right? So is that one example understandable?
Yeah, I mean, so there's a general theorem that says that in this actually goes via this result by Thoma that I mentioned, that there's always excuse me, in the universal Cstar algebra, you can always find the continuous functions on an M cell into some matrix algebra. And then we can sort of embed the torus inside that and make a counterexample this way. But it's true that it becomes very Cstar algebraic.
So
I wish I could explain it better. I'm gonna have to think about it.
So by the way, is the product of two dihedral groups one of the examples which you show is stable in dimension 2? Or is it not? I mean, I don't know your list.
I don't think it's a crystallographic group, but it is virtually abelian, right?
Right. I mean, it's the symmetries of the square tiling of the plane. Never mind.
I don't know whether I would think yes. I would think it was matrix stable.
Hey, crystallographic group, do you really mean that the action of the finite piece on the z to the n is a irreducible representation when tensor with q? Or that's not part of the definition? Like the direct product of two crystallographic group is crystallographic in your definition or not?
I wouldn't know. I don't think so. I don't. That's certainly when you get these counts of. I don't think that's the case. I mean,
so you're really talking about irreducible crystallographic group, such that the action, there is always an action of the finite top on the z to the n, and you tensor it with q, and it should be irreducible. Yeah. So Shmuel, it's mean that in his language, product of two dihedral group is not crystallographic. It's not part of the game here.
But I mean, I think our machinery should work on it. I wouldn't know.
Question whether it's stable or not, but it's not part of the theory.
So I think our machinery will work, but I don't know. Then I need to compute some K-theory, and I wouldn't know how to do that in this particular case, at least. Okay. Let me show you. So yeah, I guess I mean we kind of like the idea that we could just go through them from a beginning to the end, but somehow I'm sure we can do more than that. But there's a computation of some K-theory that is tricky, and that somehow we were lucky that we could somehow get it out of this old thesis. So I mean that's cheating a little bit perhaps. Okay, how do we? So now I'm getting ready to explain this dimension reduction argument, and also I want to somehow explain to you what is the obstruction, because sometimes we can do it and sometimes we can't, right? So that's the main thing I want to say in the remainder of the talk. And there's so Lin's proof was rather long and complicated, but not so long after there was another proof made by two colleagues of mine. So Peter Friis was a student in Copenhagen, more or less the same time as me, and Michael Rørdam is my colleague here today. They found another way of making this lift, which is very pretty. The idea is that you say that if we're looking at the continuous functions on the disk, so now I want to prove that this has the lifting property that we just talked about, then it's fairly easy to see that you can avoid points in the spectrum, essentially because the invertible elements are dense in the matrices, just because, what does it mean to be invertible? It means that the spectrum avoids 0, and you can sort of move things a little bit so that happens. So what they proved was that you can actually take this little diagram here. It's a surprising result if you think about it this way, but it has to do with the very special nature of this product modulo sum Cstar algebra. And it says that you can take as many little holes in your disk and make an extension like this. So this is always possible. So this means that you can always do this. Now, what does that mean? That means that now I punch a little holes in my square, and then I can do a retraction onto a one-dimensional grid inside of it. If I do that, then of course I make a mistake, and that's what I mean by this epsilon you see over there. but the mistake gets smaller and smaller the more holes that I have. So what they proved is that you can always do this. And the point is now that the Cstar algebra you see at the top, C of that little one-dimensional disk, this is clearly a one-dimensional nccw, so it's covered by the theorem. It is semi-projective, right? So the thing at the bottom is not semi-projective. The thing at the top is semi-projective, and I can go from one to the other by punching these holes. Now that's going to cost me an epsilon, but then you can prove that that's good enough to get matrix stability. So if you can do this for on a finite number of elements, you can find a lift which works up to epsilon, then you get the same. So this is how they prove this. And I want to contrast it with what happens for the vocalescu matrices, right? Because we know that the vocalescu matrices are not matrix stable. So this means that I know that I cannot lift this map that I've given by the vocalescu matrices. And why is this, right? So there's sort of a k-theoretical explanation. We can take k0 of everything here, and then when we compute k0 of the torus, of the two torus, that's two copies of the integers. And so k-theory for Cstar algebras comes with an order which is just given by the projections. And the order that you get here is that x comma y is positive if and only if x is strictly positive or x and y are both 0. The unit of the Cstar algebra corresponds to the element 1, 0. And then if you sort of go through what it means to have the vocalescu matrices, it means that the element 0, 1 gets sent to something which is not 0. And that explains why I cannot make this lift. Because if I had made this lift, right, so if I could put a lift here, right, this would mean that the element 0, 1 in k-theory is not sent to 0, because it gets sent to something which does not get sent to 0 by the assumption. But there is no place to send it, because this element 0, 1 is what we would call an infinitesimal. It has the property that it's less than the class of the unit, and in fact you multiply it by any number n, integer n, it remains less than 1. And it's also bigger than -1. And inside the k-theory of this product, there is no such element. So this is somehow a way of saying what goes wrong with the vocalescu matrices. That when you look at what they induce on k-theory, they send an infinitesimal of the k-theory of the two torus into a non-zero element. And then it's impossible to lift because there is no infinitesimal that I can send it to in k0 of the product. And because the map that's induced by a star homomorphism on k-theory has to preserve positivity, that's an obstruction. So I mean, this is another way of explaining what it is that Voiculescu's matrices do. And you can sort of recast this in terms of second cohomology. And actually Voiculescu mentions this. He saw that very early. And you can, there's a whole theory around this that I think is closer to what Marius is going to explain, and also in work of Schulman and Enders and Schulman, they explain that C of x, where x is a space, is matrix stable if and only if x is two-dimensional or less and has some control about the second cohomology. So you can recast this in different ways. But I want to think of it as infinitesimals, because now we can go to this Friis-Rojdam technique and we can work out what the problem is. Because now you should think of this little square that I drew is now a torus, right? So I've identified these sides here. But then when you punch just one single hole, you run out of infinitesimals in the K-theory. So this explains that for the Voiculescu matrices, where does this go wrong? Well, it goes wrong already down in this triangle here. Whereas for the second one, that's fine, because you can do these, you do these holes, you do the retraction, you get some grid, which also now is identified on the borders. So this is not flat anymore, but it's still an nccw, so you still get the semi-projectivity, so you can still make the lift as soon as you get up there. So that really is how you should think about the vocalescu matrices in this setting. And now the positive result is that if this problem goes away, you can run this machine.
Could you just say it again? It went a little fast for me.
Sorry, sure. So the point is that down at now it's the same drawing as I showed you before, but now I would like you to think of this square that you see as a torus. So you're identifying the size here and here.
Right.
When you compute the K-theory of this thing here, it has infinitesimals.
No, but I'm just trying to understand that triangle, right? So the upward arrow is just restriction, right? So that just exists with no retractions or anything.
Yeah.
Okay. Now the dotted arrow, now that isn't that dot. Oh, you're asking to extend something, and there's a K-theoretic obstruction to doing so. Got it. Okay, thank you.
And so so the statement which we prove is actually sorry.
What is the K0 of the direct product of the MNIC?
Yeah, I mean, it's complicated. It's not the product of, I mean, so the K0 of the MNs is just the integers, but K-theory it respects sums but not products. So K-theory of a sum is the sum of the K-theory, but the K-theory of a product is more complicated than the product.
So what is it? So somehow, how do you see that you cannot lift it? That's what I don't understand.
Yeah.
Well, I presume it's the first Chern class, right? Hidden somewhere.
I mean, you can compute this group, and right now I don't remember exactly what it looks like. But then you can simply compute that. You can compute the group and its order, and you can compute that no element is an infinitesimal in there.
Without really,
I'm gonna have to owe you that, but I've actually, I think it's written down in a paper I did with Marius many years ago. I can send you a reference so that you can sort of work it out. But this is somehow, the point is then that I mean these K-theories of products are complicated things, but they somehow, the product modulo sum is complicated enough that it does have an infinitesimal, as witnessed by the vocalescu matrices. So the theorem that we did, and this goes back to 98, is that we can always do this triangle down here, right? Oops, the triangle down here. If we have a two-dimensional nccw, so it's more general than just the continuous functions on a square or a torus, but it's essentially the same. We just have some functions into a finite dimensional Cstar algebras. We have some boundary conditions, making it potentially a complicated thing, which will have some K-theory, which sometimes has infinitesimals and sometimes it doesn't. If all the infinitesimals, if there are no infinitesimals, say, then this problem goes away, right? So this means that if this map, I mean, maybe that's a better way of saying it, if this map here kills the infinitesimals, then I can do this triangle. The way we phrased it is that suppose that we have no infinitesimals, or more nicely, we should say that all the infinitesimals are torsion, because the K group to the right is torsion free, so they would have to be killed automatically. But suppose this happens, right? So this means exactly that the obstruction that you get from the vocalescu matrices goes away. Then I can do this, I can punch these holes. And I can punch as many holes as I like. And then I can do, it's still two-dimensional, so it's not semi-protective, but now I can do a retraction at the cost of an epsilon, which gets very small if I have many holes. And that is a one-dimensional nccw, which we prove is semi-projective, so we can make the lift.
But
so
now,
I'm sort of,
when you are using all the time, it's two-dimensional. Do you really need that it's two-dimensional torus, or it will be with also with the surfaces, you know, like what Peter asked you at the beginning of the hour?
Yeah, so I mean, I think what he asked me, I mean, the problem here is also that the groups that he have are so, they're not virtually abelian, so they're not going to be, unless I misunderstood, they're not going to be as nice Cstar algebras as this. So I don't think I will get the opportunity to run this machine. But the boundary conditions can be as complicated as you like, as long as they sort of come from these one-dimensional nccws. So actually the base case is a sphere, where you just take the whole thing and you glue it together with one point. Then you get the bot element is the infinitesimal that has to be killed. And so we sort of prove that by hand, and then we can use that by a pullback technique. We can get the others. That's sort of how it goes. And so the point is that the PG crystallographic group that I showed you before is very easy to compute the K-theory. There's this one single copy of the integers, and because that has to be ordered in the obvious or traditional way, there are no infinitesimals. So that's going to be matrix stable. And actually, in that paper, which is 23 years old, we proved that this universal Cstar algebra was matrix stable. We just didn't realize that it was a group Cstar algebra. So this was sort of fun for me to, when I started wondering, are these Cstar algebras matrix stable, or these groups matrix stable, then I actually, in that old paper, had worked one of the cases out. So, so in the Coxeter Moser, there's these long lists of generators and relations. I don't think you'll get much out of them, but these are the groups that I'm talking about. So P1 is just set 2. Vocalescu shows you that this is not matrix stable, and PG, we just showed that it was matrix stable. And now the point is that really we just need to see if the K-theory is free from infinitesimals, and you can, I mean, yeah, so this is what, these are the tilings that you can, I mean, I found this on the internet, right? So this one is not matrix stable, and this one is fine. And then you can do this with 12 of the groups. You compute the K-theory, and they have no infinitesimals. I mean, I have to admit that somehow, you know, I had to sort of sit down and do these by hand. I don't know of a nice systematic way of doing it, but I think that underneath this is that whenever you have a glide reflection, there's some sort of non-orientability that comes in that kills the potential infinitesimals. So now they go away, and now we can use the theorem to make this lifting. And then to finish it off, so these are the ones, then actually in our old paper, we asked if our condition was an if and only if condition, having no idea of how to prove this. And then it sort of very recently, Marius Stadler proved that it's an if and only if result. And this is a non-trivial thing, because essentially, I mean, if you have an infinitesimal, you have to realize it. So you have to find some almost representations that behave just like the vocalescu matrices. And I think this is essentially what Marius has managed to do. So he proves that it's an if and only if, and then for the rest of them, you just compute the K-theory. It has infinitesimals, so it's not matrix stable, and then we're done. So I think, I mean, so for some of these groups that you mentioned, as long as they are virtually abelian in a controlled way that I can somehow hope to write it up as a two-dimensional, so it has to be, you know, virtually abelian where the abelian part looks not too different from set 2. And then if I can compute this as an nccw and compute the K-theory, then I should be able to answer if it's matrix stable or not. But these computations get weird, and of course I wish I had a more intuitive or geometric way of explaining what's going on here, but I don't really. Okay, so I'm almost out of time, so let me just mention. So this is something that we spend a lot of time on, and we have a nice result. So this now is for a general discrete group. We try to figure out when the group Cstar algebra is semi-protective, and what we can prove that if you have something which is virtually free and finitely generated, then it's automatically semi-protective. So of course we've seen things that were virtually said in the examples that I showed you, but you can do this with virtually free groups. And I would like to know that this was if and only if. I'm not going to call that a conjecture because I mean the insight I have is really weak. And then finally, it's also interesting to look at Baumschlag. Like I said too, so they fit into that concept. And actually, Dada recently proved that if you have m and n, which are not 1, that has to be bigger than or equal to 2 in absolute value, and either different in absolute value or the same, then they're not matrix stable. We did some of that as well in our paper with some ad hoc methods. So this leaves open the case of m minus m, and also 1 comma n. That's an intriguing question that I'm leaving you with not having any good ideas for how you attack this. So actually the BS1n is particularly interesting because the Cstar algebras that are associated, they're actually relatively well understood. So we might have a shot at that. I don't know exactly what to expect here. Okay, let me stop here.
Mm-hmm. Let me just mention that I think, I haven't checked it carefully, but I think that the machinery in my paper with Schiffer, Glebsky, and Tom should enable us to prove in a different way that virtually abelian groups are stable by proving that the second cohomology for Banach, for every Banach space, there is 0. And then I think it should, this machinery, but I don't think it can work for these groups, for the Baumschlag solitar, because I guess we don't know much about their cohomology. But it's an interesting challenge. You see,
okay.
So the Baumschlag solitar 1n is not, the stability is not known for the operator norm?
No.
Oh, that's interesting. Actually, now I think about it, we don't know it either for the others, except of the, we know its stability for permutation, but we don't know it for all the other norms. It's kind of interesting, at least up to now, the feeling is that to be stable for the operator norm is the most difficult in some sense. And I think Schulman showed as a result that for a amenable group, if you are stable in the operator norm, then you are automatically stable in the Hilbert-Schmidt norm.
I think that's right, yes.
As far as I know, we don't know anything. I mean, we know examples which are, of course, like the Z-C, right, which is stable in the Hilbert-Schmidt and not stable in the operator, but I don't think we know any example of a non-amenable, which is the opposite. Yeah, there are many.
I think, I mean, this is sort of where.
What? Yeah, sorry. Yeah, you wanted to say something. Sorry. Soren, you wanted to say something?
No, I thought. Excuse me. I thought I heard a question. I mean, the point here is that I think we might have a shot at the BS1n because the Cstar algebras are actually relatively well known, so you can maybe hope to throw some of the semi-productivity type of results at that. But you know, this is the weakness of my approach, is that somehow I have these Cstar algebras and I need to know something about them before I can do so. It's a little bit indirect, but then sometimes it gives you something that you, which is all of a sudden fairly easy.
So I guess that the semi-projectivity, now your lecture helped me a lot because now I understand the connection with the semi-projectivity and the stability, which I saw in the paper, but I have not digested it. But it's kind of, it looks clearly that this is a bit too strong for the stable, right? You need semi-projectivity in a very, very special case, right?
Yes. Yeah, so actually you can prove there is a concept called weak semi-projectivity, which is essentially the same as semi-projectivity, but the lift is only up to epsilon. And that translates to a product modulo sum lifting thing. But for general things, I mean, I'm only looking at products modulo sum for matrices in what we discussed. So there's something called, I mean, so what I call matrix stability, maybe I should call it, that would translate to something like weak matricial semi-projectivity. But there's also a concept of weak semi-projectivity, which is lifting from product modulo sums to products for arbitrary Cstar algebras. This is also a standard notion. And we have a little bit in our paper about this, but we don't know very much. I mean, this is sort of in between semi-projectivity, which is very strong, and matricial weak semi-projectivity, which is relatively weak. We have this in between, but frankly, we know very little.
And all of these results really require understanding the algebra up to isomorphism. There's no, I mean, if you have some kind of, I don't know, KK equivalence between algebras, I mean, is there any way of, you know, dealing with more exotic groups that way?
I mean, I think essentially, so Marius's work, I think, goes through KK. So somehow you have these KK classes that you can prove their existence, and then you can take them apart into approximate representations.
Right. So that's for negative results.
But that's sort of
right?
negative, yeah. So for positive, I don't think this has been done.
Mm-hmm.
But we do this all the time. I mean, this is really essentially in the classification theory for Cstar algebras. Essentially, we have results of the type that we have two Cstar algebras that have the same K theory, and then using a UCT, there's a KK class between them which is invertible. And then by some heavy machinery, you can trade that in for a star homomorphism. So it's a kind of thing that we do in classification, but I just haven't seen it. I don't know.
Because I was thinking that would be what you might want to do for, again, this question about surfaces of higher genus, because then you could look at the continuous function on the surface, which looks like it's two-dimensional. So if I've understood your talk, that would make me really cheerful. Yeah. But on the other hand, there's a KK equivalence between those because of Baum-Kahn for hyperbolic things. Right.
Exactly, and I don't think we have the toolbox to do this. But maybe we haven't looked hard enough. That of course would be very satisfactory. Yeah, I don't want to be overly optimistic.
Okay.
Some more questions. Okay, if not, Soren, we will all thank you. I learned a lot from your talk. Thank you very much. And Shmuel, next week we will be able to ask you questions. So you will be Shmuel will be the speaker who will give us, in some sense, a different approach or a related approach to these type of problems from a different angle.
Well, I won't say anything new. Everything will be old.
Well, old is good. Thank you very much. See you next week.